Okay, let's unpack this. Today we're doing a deep dive into, well, maybe the simplest platonic solid, the tetrahedron. But it turns out its balancing act is surprisingly complex. We're talking 4 triangular faces, but how it settles, that's the puzzle. Our mission here is to track this story, right from a tricky math proof to the, frankly, shocking difficulty of building a monostable version. That's one that only ever rests stably on one specific face, no matter what. And just so you know, this deep dive is part of our Intellectually Curious podcast series, sponsored by embersilk.com. So this whole thing kicked off, back in the 60s with Conway and Guy.
That's right, 1966. John Conway and Richard Guy, 2 mathematical giants, they asked. Could a homogeneous tetrahedron, perfectly uniform weight throughout, could it possibly be stable on just one face?
And the answer came pretty quick.
Relatively, yeah. By 1969, it was proven. No. A uniform one, it has to be stable on at least 2 faces. Simple as that. But what's fascinating here is Conway didn't stop there. He immediately pivoted. What if it's not uniform, unevenly weighted? He actually believed that was possible. But proving it mathematically, or building one, that took decades. It just remained a conjecture.
Okay, so uniform is a no, but uneven, maybe? Who eventually cracked the theoretical side for the unevenly weighted one?
That breakthrough came much more recently, led by Gabor Demokos. You might know him from the Gumbuck discovery, that self-righting ship.
Oh, right, the Gumbuck.
Yeah.
Very cool. So what was the key for the tetrahedron?
It boiled down to a combination of geometry and very precise mass placement. His team figured out the tetrahedron needed what's called an obtuse path.
Obtuse paths.
Yeah, basically 3 edges in a row where each pair meets at an angle greater than 90 degrees. Obtuse. This specific geometric feature is critical. It ensures that if the tetrahedron lands near an unstable point or edge, gravity inevitably pulls the center of mass away. It forces it to sort of tumble towards this tiny specific region inside the loading zone, which is the only place where the center of mass allows it to be stable.
Ah, okay. So the shape itself kind of guarantees instability everywhere except that one spot. Clever. But here's where it gets really interesting for me. Theory is one thing. Building this, it sounds incredibly demanding. What did the numbers say?
Oh, the engineering requirements were extreme. The math, the numerical models, they showed that for this to work physically, the heavy part needed to be denser than the light part by at least 3 orders of magnitude. We're talking a factor of 1,000, maybe even 5,000 times denser for certain configurations.
5,000 times. That's staggering. That's more than the density difference between like styrofoam and lead. What did they end up using?
Exactly. They needed extraordinary materials. They constructed a frame like a skeleton from incredibly light, hollow carbon fiber tubes, almost weightless. And for the heavy core, they used tungsten carbide. It's significantly denser than lead.
Tungsten carbide. Wow. And I bet the assembly had to be perfect.
Absolutely perfect. The tolerances were minuscule. Get this, one of their early prototypes failed. Why? A tiny stray glob of glue. It weighed less than 1/10 of a gram, but it was enough to shift the center of mass just outside that critical loading zone, ruin the whole effect.
1/10 of a gram. That glue story really drives home how tough it is to bridge pure math and physical reality. Okay, so they built it. Phase D is the stable one, right? But stepping back a bit, is this just a fascinating geometric curiosity, or does it actually connect to, real-world problems?
Well, if we connect this to the bigger picture, yes, it definitely does. Studying these ideally weighted, inhomogeneous polyhedra gives us real insight into the stability of more complex, non-convex shapes. Think about spacecraft, for example. We've seen recent lunar landers, like the Nova Sea Odysseus on the IM-1 mission. It tipped over after landing.
Right, I remember that.
It essentially rolled onto its convex hull. That's like the shape you'd get if you shrink-wrap the lander tightly. These polyhedra models help us understand why things with irregular shapes and weight distributions behave the way they do when they land or tip.
So, understanding how this perfectly balanced tetrahedron works could help design landers that maybe naturally right themselves.
Precisely. It informs the design for passively self-righting systems, making sure these expensive machines stay upright without complex mechanisms. It's about designing stability right into the shape and mass distribution.
So what does this all mean? We've gone from a 1966 mathematical question through some really advanced geometry to building an object requiring space-age materials and glue spec precision.
Exactly. And here's a final thought, something provocative for you to consider. The math actually predicted 2 main ways this tetrahedron could fall and settle type I and type II patterns. The physical model they built, that demonstrated type 1. But to achieve the rarer, more complex Type II falling pattern, the calculation showed the heavy core would need a density of around 234 grams per cubic centimeter.
234 GC-meter. Isn't that impossibly dense?
It is. That's denser than any known material on Earth, by a huge margin. It makes you wonder, doesn't it? How much of what seems like pure mathematics, pure geometry, is actually constrained by the fundamental physical laws and materials available in our universe? Where does abstract possibility hit a physical wall?
A fascinating question indeed. Thank you for joining us on this deep dive.